Hello, everyone. I'm Daniel, and I'm going to talk about a game of quantum advantage, linking verification and simulation. This is joint work with Raul Garcia-Patron at the University of Edinburgh. For reasons that will become clear in a few seconds, I should also mention that none of us has any affiliation to HBO. And this talk is based on a paper with the same title as this talk, if you're interested in more details. So I should also warn you that this is a NISC talk, but with proofs. So in particular, whenever I speak about verification, I do not mean it in the spirit of other works on verifications like the one by Mahadev and others, which really require the full-scale fault-tolerant computer. I'm talking more about how to verify the current claims of quantum advantage we're observing. Because in the last few years, we've seen many claims of quantum advantage, which were followed by disputes and rebuttals in the community. So it is fair to ask who will claim the Iron Throne of useful quantum advantage? And have we reached quantum advantage yet? Certainly not useful quantum advantage. And I must say that I'll embrace a Game of Thrones theme throughout this talk after one of our colleagues remarked that the title of our paper really sounds like a Game of Thrones novel, and I must agree with him. So thanks, Nicholas, for pointing this out. And there are four guiding questions in this work. The first one is, can we actually formalize this process we've been seeing in a couple of years of one party saying, oh, I have this very powerful quantum computer that no classical computer can even compete with, and then other people come and say, no, this is not truly the case. So can we formalize this, and can we learn something from such a formalism? Can we actually then prove something about quantum advantage if once we have such a formalism? And our third question is, can we actually efficiently verify the current quantum advantage claims? Because they really require a supercomputer and a lot of computation time to be verified. Is there a better way, or is this fundamentally infeasible? And last but not least, we also ask ourselves the question, is the fact that verifying is so difficult intimately related to the fact that we cannot simulate these proposals classically, or is one verification possible without the other, namely difficult simulation? Okay, so to answer the first question and formalize the whole idea of these claims of quantum advantage and rebuttals, we're going to propose the following game with two players. The first is Littlefinger, who claims to have this very powerful quantum computer. The other one is Tyrion, who is skeptical about the power of Littlefinger's computers. He says quantum computers, he says they're too noisy and too small. So he believes that whatever Littlefinger can do with his quantum computer, he can also do with his upscale desktop computer. So Littlefinger goes out and claims that he can sample from a distribution that Tyrion could not sample from on his classical device. And he then says, oh, I'm sampling from this device, this circuit, and so on, and announces that or claims that Tyrion could not mimic that. And then Tyrion is very skeptical about this claim because of the noise levels and so on. And then he proposes a counter distribution, namely, he says that actually Littlefinger is just sampling from the uniform distribution, that this is indistinguishable from what Littlefinger is actually doing. And then Littlefinger, being the person who is making the extraordinary claim, namely that he has a device that can beat all our classical devices, she should be the one that provides evidence that this is indeed not the case, and Tyrion demands evidence that this is not the case. So the game then works as follows, which is a game in which Littlefinger tries to convince Tyrion that he actually has all this power, or then Tyrion can actually prove Littlefinger that he's not as powerful as he thinks. First, they agree on a set of parameters for the game. So More specifically, they accept on an error parameter epsilon, which is by how much they are okay with Tyrion being able to sample from a distribution and still say that it's as good as Littlefinger's. So in some sense, this epsilon is how close we want that the distributions that Tyrion and Littlefinger are sampling from are in total variation distance. And they also agree on a failure probability delta. And this failure probability is related to how much they're willing to tolerate some false positive for this test, that indeed Tyrion or Littlefinger are sampling from a much more powerful distribution. So once they agree on the parameters of their game, Littlefinger needs to propose a function. This is the first step of the game. So after Tyrion has disclosed his initial guess for what Littlefinger's device is actually doing, then Littlefinger has to disclose a function that distinguishes whatever Tyrion is doing from what he is doing. So right now we're not imposing any sort of bound on how complex this function is. We are not also saying how Littlefinger should find such a function, but as he is making this extraordinary claim, he should be the one that actually falsifies Tyrion's claim that he's actually doing something pretty simple. And the interpretation of Littlefinger finding such a function f1 is that it certifies that whatever he is doing is at least 2 epsilon away from what Tyrion is doing in total variation distance, the distributions that are sampled from. Now, then Tyrion is of course allowed to react to this move by Littlefinger. So he then sees this new evidence that indeed whatever he thought that Littlefinger's device was doing was not his first proposal, but he can still suggest that Littlefinger is actually doing something much simpler and update his guess for the distribution, but he has to update his guess accordingly to evidence. So he has to find a distribution such that he is sure that at least for the one function Littlefinger chose before, he can reproduce the statistics. And after that, what happens is some sort of checking round. And in that round, they both send samples of their distribution to a third person, namely Daenerys, who is the referee. She then looks at the samples she gets from both Littlefinger and Tyrion. And then from that, she computes the empirical average of both of F1 under these 2 distributions and checks that they are close. And if they're close, then, well, the devices are in principle indistinguishable given the evidence seen so far. Now that we've seen all the steps of the game, if Tyrion was successful and the distribution he is sampling from can actually match Littlefinger's statistics, then Littlefinger needs to propose another function to again falsify Tyrion's claim that he can easily simulate whatever Littlefinger is doing. So we then just iterate this procedure a couple of times and a few things can happen. So first, it might happen that Littlefinger cannot find the function that distinguishes whatever he is doing from what Tyrion is doing. And in that case, Littlefinger loses because, well, in light of all the evidence, there is nothing that Tyrion can't do that he can do. So he lost the game and he has not proven quantum advantage. On the other hand, it might be the case that at some point, Tyrion is not able to either find a probability distribution he can sample from that actually reproduces the expectation values of Littlefinger's distribution, or it might also be the case that he just knows whatever Littlefinger is doing, but he cannot sample from the same distribution with his device. And in this case, he loses. So either he doesn't find the new distribution to sample from, or he cannot sample from that distribution. And in that case, he just loses. So these are the possible outcomes of the game. So let us analyze it in a very simple scenario, namely when we have an instance of a useful quantum advantage. So let's say Littlefinger claims that his quantum computer is better than Tyrion's classical computer to find, for instance, the ground state energy of some classical Hamiltonian H, which is encoding some very hard combinatorial optimization problem. And in this case, the choice of the function that Littlefinger should choose is very clear, namely the energy of the strings he is outputting. Because if the states he can sample from have an energy density that is smaller than the ones that Tyrion's is sampling from, well, by at least epsilon, then indeed this function will be enough to distinguish his output from Tyrion's, and he will win. On the other hand, of course, if Tyrion can actually reach similar energy levels as Littlefinger's, then there is no proof of quantum advantage. Now, this is a very simple, straightforward scenario. Let us now talk about another example, namely the case of random quantum circuits. And right now, the approach to verify or benchmark random circuit sampling is a so-called heavy output generation problem, and verifying this takes exponential time. And essentially what is done is to look at this function over here, which essentially computes the expectation value of the probability of the outcomes you're sampling from. But I mean, with respect to the ideal quantum circuit. And the goal is somehow to sample from strings that have higher than average probability, okay? And if you have the uniform distribution, one can show that if you're sampling from that distribution, then the expectation value of this quantity over here is 0, whereas if you're sampling from the ideal distribution, this is 1. So in some sense, this function over here allows us to distinguish the uniform distribution from the ideal distribution. And whenever you obtain a higher, so you can also use this score to quantify how well you're doing. Now, recently, there was a very famous quantum advantage experiment by the Google group, and they've reached a certain value of this cross entropy benchmark or HOG. And this can be seen somehow as the first round of our game. So the first round of our game was they claimed they were sampling from this random quantum circuit and that nobody could reproduce the expectation value for this function they were actually observing. Okay, and just a side remark, actually this function is not between -1 and 1. You have to work a bit to get rid of this technicality, but let's push it aside for now. So we can see that this could be seen as somehow the function we look at the first round. And then recently in 2021, Pan and Zhang claimed to simulate the quantum sycamore circuit. So what is their strategy to do so? First, they fixed a few of the outcomes of the circuit to be 0, okay, which significantly simplifies the underlying tensor network contractions you need to perform to sample from the circuit. And then they just searched, brute force the whole space of outcomes conditioned on those outcomes they fixed being 0. And then they look for high probability strings on that subspace and post-select on those and sample from those. Of course, and this way, they actually reached a even better score for this cross entropy benchmark than the Google team. So in principle, they were able to pass this first round of the test. But then Littlefinger can then actually, or Google can actually propose a second round. And there is one simple way that Littlefinger can actually show that whatever he is doing is not what they are doing. So what he can do is just to pick the function, which is 1 if the outcome at qubit I is 0 and 0 elsewhere for all qubits. And if you're sampling from a random quantum circuit, then the 1-qubit density matrices, reduced density matrices, are actually pretty close to the maximally mixed state. So the expectation value of this function on an output of a random quantum circuit, likely also to be the case in the noise scenario, is roughly 1/2. Whereas for this distribution that they're sampling from to spoof Google's claims, this will be 1 for certain qubits that they have set, right? In this case, you can easily distinguish his distribution from this other one, and then the ball is back to Tyrion to show that this is not what he is doing. So we see that in the case of useful quantum advantage, the choice of the functions is clear, and for more like proof of principle cases like random quantum circuits, these many rounds can actually also allow us to distinguish whatever these quantum devices are doing from some attacks, right? Okay, now that we have a definition for a game, of course, one very reasonable question is, what is a good strategy for Tyrion? So we'll mostly focus on Tyrion's side and not Littlefinger's side on how to find the functions and so on for the rest of the talk, and try to help him find a good strategy. And one observation is that NISQ era distributions or quantum advantage distributions, they are very high entropy distributions, and this is either without or with the noise that is inherent to NISQ. So Tyrion should exploit the fact that he knows that in the NISQ era, Littlefinger's device is likely to have high entropy. And then one framework which might lead, which will show is useful in this case, is then that of mirror descent for Tyrion's distribution. So mirror descent then with the von Neumann entropy as potential then suggests that Tyrion should sample from Gibbs states like this one. So the exponent is just given by the functions that Littlefinger proposed. And why is that? Well, because this will converge very fast for functions of high entropy. So here we have the relative entropy of the target distribution with the uniform distribution, which is very small if the entropy of this distribution is large. So we see that the mirror descent will converge very fast if we know that this quantity over here, this relative entropy, is small, as we expect to be the case in this distribution. And on top of that, this distribution that Tyrion is sampling from will have the property that the expectation values of all the functions in the exponents will be small if we update them often enough. So by picking distributions of this form, Tyrion will be ensured that they will have the right expectation values, and he will be able to exploit the high entropy of NISQ in quantum advantage distributions. So what happens if Tyrion actually uses this strategy against Littlefinger for the examples we discussed so far? So in the useful quantum advantage scenario, one can then see that this will lead to Tyrion actually performing simulated annealing to find low energy states. And to this day, this is a competitive and widely studied strategy to solve combinatorial optimization problems. So we see that it's not leading to a completely ridiculous idea for Tyrion in this useful quantum advantage scenario. But more interestingly, in the case of random circuits, this really seems to be a good strategy for Tyrion. So first of all, one can show that whenever one has an approximate 2 design, then the output of that circuit with high probability will have relative entropy of constant order with the uniform distribution. So in particular, if we know what the functions fi are, and again, it's not Tyrion's job to find them, then this mirror descent will converge to Littlefinger's distribution in a number of iterations that does not scale with the number of qubits. In addition, this means that he can actually sample from the Gibbs states that mirror descent proposes in this time by just evaluating the functions fi and using rejection sampling. So we see that if Littlefinger only constrains himself to functions that allow us to efficiently distinguish whatever he is doing from Tyrion's device, then he will never win. Because if the functions that are used to distinguish his device from whatever Tyrion is using can be efficiently computed, then Tyrion can also use mirror descent to actually sample from a distribution that is close to Littlefinger's. And he will always win the game. And in particular, we now shown that either the output distributions of random quantum circuits are impossible to efficiently distinguish from very easy distributions, or efficient approximate classical simulation is possible. So either we are doomed to have to resort to functions that require exponential time computation to verify quantum advantage claims, or we can actually easily simulate those output distributions efficiently. Now, this was in the scenario where Littlefinger actually provided Tyrion with many rounds, right? So he passed many rounds and provided Tyrion with many functions. But it's reasonable for us to ask if Littlefinger could even just pass the first round if we restrict them to efficient functions, right? And that is just asking the question, can we distinguish from the uniform distribution efficiently, namely the outcome of a quantum random quantum circuit and the uniform distribution? And Gunn and Aronson in 2019 conjectured that actually both estimating the outcome probability of quantum circuits and also fooling this benchmark, this heavy output generation benchmark, are exponentially hard for classical devices. But of course, this heavy output generation also provides a way of distinguishing from the uniform distribution. And what we can then also show is that whenever you have a function that can actually distinguish the uniform distribution from the output of a random quantum circuit, then that can also be used to spoof the heavy output generation problem. So if we believe this conjecture that fooling this heavy output generation problem is hard, then even distinguishing the outcome of a random quantum circuit from the uniform distribution efficiently is a hopeless task. So in particular, we show that whenever you have a function that distinguishes the uniform distribution from the output of a random quantum circuit, then again, by resorting to simple rejection sampling, you can find heavy outputs of the function of the distribution using F. And the idea is essentially, again, resorting to the fact that the outcomes have very high entropy. In this case, it's a Renyi entropy. And one can then show that if you have two distributions that have very high Renyi entropies, essentially maximal, like is the case for the outputs of random quantum circuits in the uniform distribution, then that function has to be supported on exponentially many strings. So only a fraction of the state space can be zero. And then you can easily find points on the support of F by sampling at random. And then if you take the distribution that corresponds to the uniform distribution of the support of F, you can show that that function, this distribution actually spoofs the heavy output generation problem for the random quantum circuit. And in parallel, this can be easily sampled from by what I mentioned before, because it's not difficult to find points in the support of F. So in conclusion, we see that this game gives us some useful formalism to model near-term quantum advantage, it allows us to show some interesting claims, namely, for instance, that either verifying whether a quantum device is doing something completely trivial or something very hard, very likely requires exponential resources. And the alternative to that is that efficient approximate simulation is possible for these random quantum circuits. And many questions remain open, of course. So, for instance, is it possible to still obtain quantum advantage claims without having to sample from such high entropy distributions? This would require new proof techniques, of course. And it would also be interesting to see if we can actually find attacks on quantum advantage claims based on this game and the strategy we outlined for Tyrion. And before I thank you for your attention, I just would like to summarize the current state of affairs like this. So you have one person claiming to do something incredible and unimaginable, but the other, if you take the stand and say, oh, I don't want to spend a couple of thousands of dollars verifying what you're saying to me, you're just flipping some coins, then there might be no way of getting out of this dispute, which is rather frustrating. And with that, I would like to thank you for your attention.